Hi everyone, today we're going to study equivalence class. Let us define equivalence class. Let R be an equivalence relation on a set A. The set of all elements that are related to the element A of set A is called the equivalence class of A and is denoted by this symbol. The equivalence class of A has elements S such that the ordered pair A-S is an element of R. For all S, an element of set A. The general case is to find the equivalence class of A of the relation congruence modulo M. With this, our symbol can be written like this. The subscript is M, and we read this as equivalence class of A of the relation congruence modulo M. Writing now the elements of this, we can write the first element to be that A. On the right of A, the first element will be this A plus M. And the next element will be this value A plus M plus another M. So we have A plus 2M. This pattern will continue going to the right. Now for the elements on the left side of A, the next element here will be the A minus M. Prior to this, the element would be A minus 2M. And prior to this, the element will be A minus 3M. So this pattern will continue for the elements going to the left of A. Now let us see some examples. Example 1. Consider the equivalence relation on the set X with elements from 1 up to 10, defined by X is equivalent to Y if and only if 3 divides X minus Y. Find the equivalence classes. Let us write the first equivalence class. Considering the first element here, the first equivalence class is here. Equivalence class of 1 of the relation congruence modulo 3. Writing the first element, that will be this same number 1 will come here. The next element will be 1 plus 3. That will be 4. Next, 4 plus 3 equals 7. 7 plus 3 is 10. If we add 10 plus 3, the sum is 13, but that is out of the range of the set. So the elements of our equivalence class 1 are 1, 4, 7, and 10. Next is equivalence class of 2 of the relation congruence modulo 3. The elements are starting from 2, 2 plus 3 is 5, 5 plus 3 is 8. Next is equivalence class of 3 of the relation congruence modulo 3. The elements are starting from 3, 3 plus 3 is 6, 6 plus 3 equals 9. We shall continue to write the equivalence classes for 4 up to 10. While doing so, you will find out that this equivalence class 1 is equivalent to equivalence class 4, which is also equivalent to equivalence class 7 and is equivalent to equivalence class 10. Also, that equivalence class 2 is equivalent to equivalence class of 5, which is also equal to the equivalence class of 8. Likewise, the equivalence class of 3 is equal to equivalence class of 6 and also equal to equivalence class of 9. So, the different equivalence classes are equivalence class of 1, equivalence class of 2, and equivalence class of 3. This is the final answer. Example 2. Find the equivalence class of -1 with respect to the relation R on the integers given by R equals the ordered pair AB such that A equals B or A equals -B. Evidently, this relation is an equivalence relation. The equivalence class of -1 is given by, the symbol is here, equivalence class of -1 of the relation congruence modulo R is equal to the elements S such that the ordered pair -1 S is an element of R. For all S, an element of Z, the integers. We know that the elements in Z related to -1 by R are 1 and -1. Therefore, -1 of the relation congruence modulo R equals -1 and 1. This is the final answer. Today, we're going to study more examples about equivalence classes. Let's see this example 1. Find the equivalence classes of 0 and 2 for the relation congruence modulo 7. The congruence modulo 7 equivalence relation is defined by this. R equals the ordered pair AB such that A minus B is divided by 7 is an element of integers Z. We will denote the equivalence class of A under the congruence modulo M as this notation. A is enclosed in square brackets and a subscript M is given. Let us now define the equivalence class of 0 for the relation congruence modulo 7. As defined, the elements are S, such that the ordered pair 0S is an element of R. For all S, an element of Z, the integers. Likewise, this equivalence class is defined like this. The elements are S such that 0 minus S over 7 equals K. This K is an element of Z, the integers. For all S, an element of Z. Let us now write the elements of the equivalence class of 0. The first element will be that 0 itself. On the right side of 0, the next element will be 0 plus the modulo 7, and that will be 7. This value 7 plus the modulo 7, we will get 14. 14 plus 7 will be 21. This pattern will continue as we go on with the right side. On the left side of 0, we will have 0 minus 7, so we will get -7. This -7 minus 7 will get -14. -14 minus 7 is -21. This pattern shall continue as we go on the left side. So these are the elements of the equivalence class of 0 for the relation congruence modulo 7. Let's go now to equivalence class of 2 for the relation congruence modulo 7. As defined, the elements are S, such that the ordered pair 2S is an element of R. For all S, an element of Z. This is also defined like this. The elements are S, such that 2 minus S divided by 7 is equal to K. This K is an element of integers Z. For all S, an element of Z. Let us now write the elements of the equivalence class. The first element is the number 2. The next element on the right side of 2 will be 2 plus the modulo 7, and that will be 9. This 9 plus the modulo 7 will be 16. 16 plus 7 is 23. This pattern shall continue as we go on the right side. On the left side of 2, the first element here will be 2 minus 7, so we get negative 5. Negative 5 minus 7 is negative 12. Negative 12 minus 7 is negative 19. And the pattern continues on the left side. These are now the elements of equivalence class of 0 and equivalence class of 2. Example 2. Find the equivalence classes of 0, 1, 2, 3, and 4 for the relation congruence modulo 5. The equivalence classes are tabulated in the table here. So we have the equivalence classes for 0, 1, 2, 3, and 4 respectively. Let's start with the equivalence class of 0. This is equal to 5 times n, such that n is an element of Z, the integers. So the elements of this equivalence class are starting with 0, going to the right. So 0 plus 5 is 5. 5 plus 5 is 10, and so on. On the left side, 0 minus 5 is negative 5. Negative 5 minus 5 is negative 10, and so on. Let's go now to equivalence class of 1. This is equal to the 5n plus 1, such that n is an element of Z. So the elements of equivalence class of 1 will be here, starting with that number 1 itself. On the right side of 1 is 1 plus 5 becomes 6. 6 plus 5 is 11, and so on. On the left side of 1, the first element here is 1 minus 5 is negative 4. Negative 4 minus 5 is negative 9. These are now the elements of equivalence class of 1. Let's go to the equivalence class of 2. This is defined as 5n plus 2, such that n is an element of Z. The elements of this equivalence class are here, starting with the number 2 itself. So 2 plus 5 is 7. 7 plus 5 is 12, and so on. On the left side of 2, the element is 2 minus 5. That's why this is negative 3. Negative 3 minus 5 is negative 8, and so on. Let's go now to equivalence class of 3. This is defined as 5n plus 3, such that n is an element of Z. The elements of this equivalence class of 3 starts with the number 3 itself. 3 plus 5 is 8. Next element, 8 plus 5 is 13, and so on. On the left side of 3, we have 3 minus 5 is negative 2. Negative 2 minus 5 is negative 7, and so on. The equivalence class of 4 is defined as 5n plus 4, such that n is an element of Z. This is equal to the first element is the number 4 itself. So 4 plus 5 becomes 9. 9 plus 5 is 14, and so on. On the left side of 4, we have 4 minus 5 is negative 1. Negative 1 minus 5 is negative 6, and so on. So we have here now the elements of the equivalence classes for 0, 1, 2, 3, and 4 respectively. These are the final answers.